what we're going to have panels tonight for the. Yeah, we're going. I just put everybody. I didn't put any speaker, but we can actually talk to the IEB and say what we thought. But it's going to be like less than 5 minutes because we have tons. Oh, I was telling her next time we should have for 3 hours so that we have longer tutorial style. Okay. Half-hour presentations. So it would give people more time. No. That's fine. It's 2 hours break, 1 hour. It's great because we could do 2 hours the drafts and everything. The last hour, 2 longer presentations. That would be easy. Yeah, fine. But I would like it to be all the same because I don't want to lose people. But I think we need 3 hours. 2 hours is not enough. I think like DetNet had, they had more than one.
2 sessions.
So we should have that 2 back-to-back sessions. We're going to start because we have a really, really packed agenda. This is COIN Computing the Network, a proposed research group.
Oh, I'm Eve Schuler.
Jeffrey He.
And I'm Marie-Josée Montpetit. And again, we have a really packed agenda. Thank you for everybody who stayed over on the Friday of the IETF, where everybody is extremely exhausted, tired, and maybe, I hope we give you some energy with this new topic. This is probably you've seen it already. This is the note well about IPR and the fact also that we have to be nice to one another. I think the IETF is working extremely hard to make these meetings a safe place for people to express their opinions and express their especially technical opinions. This is the goal of the IETF. I think it's important to stress at every meeting that we are not doing standards, we're doing research. We are fostering research. We are fostering the development of research communities, in this case about this idea of distributing computing and storage and decision-making throughout the network. And again, we're never going to do a standard here, but we're going to have a lot of information and potentially experimental RFCs. So again, this is what I said. We want to foster the research. We want to look at architectures, protocols, and real work case. And like I said earlier this week, we have as the chairs a little bit of the three things. I'm an architecture. Eve does architecture and protocols, and obviously Jeffrey comes from industry, has a lot of real world, use cases and stuff. So this is our agenda. It's extremely tight, and I am very, very sorry to all the presenters who got their presentations squeezed because of time. And we promised that in Vancouver, we're going to ask for more time so that as a research group, we have more time also to dwell into the research aspects that a lot of time need a little bit more detail. So I'm very sorry. We had 2 hours and I should have asked for more, or we should have asked for more, but we're going to change that. We have, and again, following some discussion that we had at the interim, that this is not just about drafts and drafts presentation. So we decided to do two sets of presentations, what we call the research and the research update presentations, and then all the drafts presentation after. If anybody has comments about the agenda. Okay, so we're going to do this as a group here, and you can start.
Sure. We were invited into the IAB earlier this week on Colin's request to give them an update on how we're doing as a research group. And as a result, Marie-Josée gave a terrific presentation, and we got lots of feedback from the IAB. We've been around now for a year, so we've had three. This is our third IETF, and even before that, there were some side meetings and so forth. But we thought we'd share with you the feedback that we received. For those of you on the mailing list, you've seen the really detailed comments that came back, and here on this slide are the main comments. The biggest comment that we got almost from the get-go was, have you and should you give greater consideration to issues around security and privacy and trust, given that we are approaching, one, a new architecture, and two, a more distributed context within which we're doing this work. And so we got comments like, you know, to make this work relevant, you have to focus there more, as well as consider threat models and so forth, which is a little hard because we're still pretty embryonic in our life cycle as a group.
You can actually, yes. We decided to do
No? Okay, I can keep
Okay.
going.
We decided to do this a bit panel style, but okay, so let's change the panel person. I think, yes, I made the presentation, and we got a lot of comments, but they were all in the same direction of security, which is huge. But at the same time, I think, which is good for this group, and again, thank you for all of you guys who participated in last year. We didn't get anybody who said this is like a stupid idea and it should never come to the IRTF. So, you know, at least at this point, we were very happy. I think, however, there's a call to action to the whole group and to everybody who presented papers or did some drafts, and even for some of our hackathon participants, and I see them around here, is to maybe revisit what we've been doing while having the security point of view inside. I don't think, or correct me if you disagree, but I don't think it means to change anything now, or I don't think it means to change things in a very different way. It just means that, you know, when I'll get the point of packet filtering, for example. If I do packet filtering on metadata, what is that metadata? It's in an encrypted system. What does it mean? What do I want to expose to the filtering or to the inside processing? Just maybe rethink all of this with this security and this privacy aspect in mind. This said, there's a lot of us who work in industrial networks or things related to industry where this may not be as important, but I will give it back to Eve, because in edge discovery, that could be some issue.
I'm Eve, by the way, in French. Eve and Eve are the same person. In any case, it's okay. The other things I wanted to tell you about are some of the other things that seem to resonate with the IAB. The first of which was that as we started to talk about this trend towards edge computing, and we talked about what's the relevance to the IETF, for example, there was some excitement saying, yes, please. One way to differentiate ourselves from all the other efforts out there is to tie it back to what's going on in the internet, what's going on in the standards and the protocols that are so typically developed here.
And actually, after we talked to them, it made me think of some kind of imagery for it as the same that right now, or actually I've been doing IETF for so long, so I don't really remember when I started coming, but it was more like some kind of, you know, it was more like a telephone network in the way that you had these routers that were very closed and they were connected by more or less big connectivity network, you know, networks and cables and stuff. And I was thinking after we had the IAB that what we're doing right now is more taking like a computer board, breaking it in pieces, throw the pieces around and connect them, and then figure out how we can make that computer board work in the distributor. And we're talking to, no, actually I have my timer. We still have 1 minute.
Summarize. Okay, so I'm going to summarize, which is the other things besides security, privacy, and trust. We've got 1 minute. Is that we, of course, as IETF goers, come from the networking perspective. We should go out of our way to recruit those who might be coming from these other perspectives, like computing, like storage, to add to our point of view, and that we were given some very specific examples of places where we could get some guidance, including the 5G slicing context, where, you know, what have the telcos done with regards to security when you're looking at these slices of quality of service streams and so forth. And additionally, the attendant question that we always get, which is, and that we've raised as a community around, are we going to be using the same kinds of APIs that the data centers are using in order to gain access to resources?
And I don't know if there's IAB members in this room right now, but I would like to thank them for their comments. and for the time they took to allow us to talk. We were supposed to have 15 minutes, and we ended up talking for 45, and that's all my fault. So we have 7 seconds. So.
And so if you want the details, there's also a detailed set of comments on the mailing list. Runaway phone. You're actually on hold, and this is the music in the background.
Okay, it's off. Okay. So Hackathon Summary, you want to talk about it? Okay, so people who were at the hackathon, please raise your hands. I see a few around. We had a hackathon I'm talking too much. Anyway, we have a hackathon on Saturday and Sunday, and we're still embryonic in what we want to do with this. So we did mainly some stuff to familiarize ourselves with data plane programming, but we were so lucky. We ended up getting a bunch of people who actually had projects, and we did that. The first idea was to continue what we had started in Montreal and packet filtering, but then we had, again, incredible people who came with projects. And the idea that we have, and we're going to discuss it in an interim that we plan to do later, actually how to maybe have a common project. And you're Eve and not Ev. And Eve has started to actually put some words into this, so we're going to share that to the list. So this is people working. We had obviously the tutorials for people who didn't know what they were doing. We had actually Michelle, who's going to present later, who did service function chaining monitoring. We had actually two people from the Singapore community, which was fantastic. And one of them did the packet filtering for critical events, and he did it in about half a day. And we had some problems with BGP root origins validation. And actually that was good because it showed us the limitation of the language. We're using P4. They pivoted to a new project, but it also showed us that the idea that we have, and that is going to be probably expressed by other people in the presentation, that you want to use the very fast switches to do line speed stuff. And when you have something more important or more consistent, you want to send it to another type of processor. So it just confirmed a little bit what we wanted to do. And the team was all these people, and those who have a star were the first participant in the hackathon. And the good thing about this is there's actually another set of about 7 or 8 people who participated in Montreal, and they were not here, but I know a bunch of them want to come to Vancouver. And that's why we want to have maybe a more important project, so that now that we have a very good community around this, we can actually move on with a real project. And also, I will tell you that I think it was very good for us to have the hackathon because it also allows us to recruit people that may be interested in the work of the group.
Okay, quick drafts update. So we've got actually a total of 8. These are the first 4. We've got them listed in chronological order. You're going to be hearing today, the first 3 that are listed are ones that were not updated. The bottom one also is not going to have representation today. It was presented last time, but they, in their work, they updated their section on application packaging and programming frameworks for decomposing at runtime. And they interestingly also cited that one of the outcomes that they're hoping from their draft is just basically a research roadmap. How do we go forward? Okay, these are 4 others that we have. And although we won't be hearing from the industrial use case, they updated their draft in the security considerations area, and also for traffic filters. We are going to hear from them today for the transport protocol issues, and we are also hearing from the other 2. So we will wait till later in the session. Some points to note: the fact that we've got 8 internet drafts actually stood us pretty well with the IAB, that there are people interested in this topic, and it's our intention that if we get progressed, from a proposed RG to an actual RG, that we will look at the most mature of these, try to advance a couple of these to be taken in, begin the process of taking these in officially into the working group, the research group. So we'll wait to give you the outcome of whether we were blessed or not officially, and then start down this path of ID incorporation.
Okay, so we can start with presentations without further delay. And actually, this is the same advice we gave in Montreal, is actually when you present, can you, if it's clearly in your slide, it's great. If it's not, well, maybe just highlight how you relate to this chart, to our charter and to the cloud to edge continuum. And the first presentation is Jörg. Okay, so hold on. You have to,
Do you have a clicker for me?
We do.
we do, and we have your slides.
Perfect. Oh, this is. Can you turn this into presentation mode?
Wait, I'm getting there.
Okay. Hooray. Yeah, thanks. So I just realized that I'm doubly wrong here. First of all, I'm not in the this is not in the focus of this research group. Apparently, it's not core to edge. It's probably edge or falling off the edge. And then I don't have anything on privacy, security, and trust. So maybe this is yet to come. Still, I want to talk about two different bits in this.
Jörg, this is research. You can actually expand your research.
Okay. I want to talk about two different bits in this talk. First of all, I want to give a brief idea of two kinds of little systems that we built for in-network computing, and then I want to relate this, hooray, including specific slides, to several aspects that relate to edge computing, and not edge computing, in-network computing. So quick context. So this is about IoT. On the one hand, so this means that we are not looking at generic VMs or rack servers that have arbitrary compute capabilities, but we are looking at specific devices that have certain capabilities that others might not have, which also means that they are usually harder to scale. So you just can't put up, or there's no point in putting up 200 or 1,000 temperature sensors next to each other. We are also talking about mobile users, which means that we don't do orchestration according to RTT minimization or overall global load balancing, but there is a certain locality relevant here. So if I'm trying to control temperature in this room, luckily this morning it doesn't seem to be necessary because the system seems to be working. Then I want to interact with what's around me, not with something that's at the other end of the city or in a different room. And thirdly, we are looking at relatively fine-grained functional decomposition. And fourthly, if I'm coughing a bit, this is the impact of this air conditioner, and I'm sorry for this if this hurts your ears once in a while. So we have two models of code provisioning fundamentally that you could take apart. One is cloud-driven, which is what Marie-José alluded to earlier, where this is more the CDN model, where application service providers offer code in a centralized manner to instantiate this in the edge, in other network elements and so on. And we can also look at the user-driven organization where code actually comes from the user. And by this, I don't mean a user invoking a certain function from an app, but actually defining or programming the environment, programming the world around them with this respective function. What this usually looks like is that you have your mobile phone as your preferred device or something else, and look around what kind of devices you can possibly find. Figure out which of these you are currently interested in for the app you are trying to realize, for the function you're trying to execute, like temperature control. Compose them, make use of them as you see fit. This can be done either by calling functions that are already available on those devices or by instantiating code on sensor devices that are then supposed to do to carry out the task on your behalf. So like mobile code. So I have two examples that follow this idea. One is a Lua-based mobile code execution environment, and the second one is a trigger action framework leveraging BLE beacons. Both are client-driven in that whatever is being programmed comes from the user device, comes from the users. We don't interact with monster things, but we interact with ESP32 microcontrollers that are sufficiently lightweight, cheap, and can be there plentiful. And we don't use network infrastructure at large, but we restrict ourselves at present, due to this earlier mentioned mobility case, to broadcast networks with strictly local service discovery. So we are using beaconing in both cases to find things. Let me quickly start with number one. So this Lua-based mobile code execution environment, you can see this monster picture there. There's a small node that looks like a smartphone moving along a dotted line from the left to the right. And it's the fundamental idea is that it's going to pick up signals from devices around it, including their capabilities, and then makes use of the devices that are currently in reach. If a device goes out of reach and another one comes in, it's going to adjust, leaving all services behind, instantiating functions on new devices. There could be an internet backend, but we are not going to talk about that today. These individual nodes that the mobile device interacts with have a certain architecture. I've already mentioned that this is an ESP microcontroller. So this thing runs at the bottom, an ESP. Then we have an RTOS on top of that. And on top of this, again, we have a bunch of C-based drivers, bindings to the Lua language, and then our Lua execution framework. That gives us the blue box on the left-hand side that provides drivers to interface to actuators and to sensors, turning on lights, measuring temperature as simple examples, has interfaces to local storage and has interfaces to networking so that these things can talk to each other. So fundamentally, this is where we are using Lua process VMs. They offer a generic code execution platforms. We send our Lua scripts as strings attached with metadata of what kind of resources they are going to require, so that a device can actually make a sensible decision whether it can sensibly execute that code and whether it has all the necessary resources. This generic mechanism gets combined with specific sensing and actuation hardware, which are defined as user or device-specific capabilities, so that our mobile devices can sense which devices and their surroundings it should actually be contacting. The function properties, in the sense of functions being executed inside the network, are made available via Bluetooth beacon, where the nodes describe what kind of features they can offer. And they also provide rendezvous information, specifically Wi-Fi SSID to connect to for the mobile device. Function execution, so mobile device then essentially goes off, picks one or more nodes that it would like to talk to, and transfers the mobile code. The node itself can then decide whether it has the necessary capabilities and it has enough resources in terms of compute power available at the moment, and can either decide to refuse execution or accept that script. The instantiation then happens on the executing node, and at some point the mobile can collect the results. We support two different modes of operation. One can be one-shot interactions, fetching data. The other one can be instantiation of code that runs in the background and, for example, triggers updates every k seconds. So this whole thing looks like then a two-stage process, where on the one hand we have a script collection and distribution networking interface that puts scripts into a local queue from which the runtime environment picks what they can execute next, providing some kind of serialization, but there's also some degree of parallelism supported. How many minutes have I gone now?
You have 7 minutes.
Not too bad. So we built this, tried this out, got roughly the idea that usually, at least with the fairly poorly optimized Wi-Fi connectivity, the slowest part at the moment is actually discovery and code instantiation. That gets a bit better if you transfer multiple scripts in one run. But the entire thing is sufficiently lightweight that we figured by extrapolation that a single of these little microcontrollers can support something like 100 user devices. The second part, so this was point-to-point communication. A mobile node talks to an individual infrastructure node and then offloads something and then programs them one by one. The second part is a bus-based approach where we essentially have built a distributed if this then that trigger action framework. On the left-hand side, you see trigger drivers, which essentially can consider to be sensors, hardware sensors that generate signals whenever a certain reading temperature, whatever. On the right-hand side, we have action drivers, which are the equivalent of doing something. And in the middle, we have two blocks. One is something like a Boolean circuit that can express sophisticated if this then that logic, saying, okay, if a certain set of conditions are met, I want to have a certain thing to be executed. And then we have a separate matching of what a specific output to which devices or to which actuators this output should be forwarded. That's roughly the overall architecture in terms of which gives us a similar, in terms of the in-network compute, we have essentially distributed triggers and actions. We have our code is the program logic that we distribute. Function properties are essentially globally unique device identifiers, and then instance IDs to refer to specific instances, as well as definition IDs to provide more complex functions, so we can actually provide some abstraction in terms of programming. We utilize BLE beacons as a bus system, so this is actually essentially used for everything. We use this to discover nearby devices and their capabilities, to learn about what features they can do, to spread rules and all these little programs, and then once those are spread and loaded, to also execute the respective triggers and have the triggers flow across the network. So this comes back to my says mentioning breaking up a board of a computer and having things flow back and forth between the individual bits and pieces. To some extent, this is a bit on the extreme side, because we only move computation, no data at all. The only thing that gets moved is individual trigger signals. There are a bunch of protocol messages. They are sufficiently squeezed so that they can be and efficiently represented so that they can fit into Bluetooth low energy beacons. I'm not going to go through those in detail. In the end, you get something like a model where you have a bunch of sensors in the environment. You can have multiple mobile nodes that are running around. They interact with these, find out which capabilities they have, can then spread triggers, rules, and actions and these little programs, and thereby actually connect those entities together and then go away, and these things can continue talking to each other, self-orchestrating them in the end according to what the mobile devices programmed them to do. There are many interesting little issues here in terms of how do you deal with conflicting rules. What do you do if you have 20 different users in parallel and they want to do? There's fairness issues to be discussed and so on. So we are currently exploring the basic invocation principles. These other systems and operations issues are on our to-do list, but not all of them have obviously been solved at that stage. But we have running prototypes for this as well, again on an ESP32. So putting this briefly into the context of the working group, and I'm going to skip through most of the remaining slides in the interest of time, but I want to, this is also something one can easily read up in the end. Originally I had 5 minutes more, so forgive me. Our take is that we have roughly 5 steps when it comes to in-network compute operations, right? We need to define what kind of functions we have, what kind of properties they have so that they become identifiable. Next, we'll need to be able to discover those, be it in a local environment as we showed, or in a network environment using any casting or whatever. So this is where we have our little instances of functions called G and next to discovery. Then an orchestrator, a client, or whoever would be responsible for picking which of these functions should be executing a particular program or a particular workflow at a given point in time. And then if we have multiple of these, they need to be orchestrated and linked up. And then in the end, we have an execution step in which those different code needs to be transferred, execution flow needs to be transferred, and so on. I have individual ones for each of these different steps. For the two examples, we'll probably fold some of this into our architecture draft or something similar in the end. Let me conclude this short presentation with, so this was an example for in-network computing for broadcast networks. Of course, discovery and things like this can also be extended to go beyond simple broadcast networks. This gave us a good starting point to build stuff that works purely locally, but that is of course not restricted to this. There are two interesting meta aspects I want to raise. One interesting bit that's worthwhile looking at in future work is especially in the second case, but also in the first one, we push control explicitly into the network, and then the user can go away and let the network autonomously act as a computer and do what we would want it to do, which probably comes closer to running a daemon process or some background thing in the end. That of course brings all kinds of operations and management issues that would need to be considered in the future. And then we have a similar question that the IoT folks, when it comes to data semantics, have been discussing at length, that we also need to figure out how to describe semantics of APIs with signatures and the like, in order to allow this composability across different functions inside the network. And that's it.
We have time for one question.
Lucky me. Eric, not Mark. So any thoughts on how you name the different objects? So the inputs to your triggers and your actions, right? Are those named relative to the environment, relative to a particular device?
In these cases, the moment we distribute our own scripts, you get an implicit name, right? I'm invoking something on a given node. So this is that is capability driven. I'm not naming functions. I'm looking for device. So this is essentially an attribute-based addressing that we are doing here.
So you're asking about the temperature. The temperature is something that you're looking at, not the temperature on that device or the temperature in Singapore.
Right. Given that we have in the specific temperature, in the specific trigger action case, we have a class of temperature drivers. So they have a common identifier. They all provide the same kind of data object as an output. So you would essentially find which devices offer this kind of a sense, this kind of a feature by comparing this. This is right now, in this specific case, it's numeric IDs simply because we need to be concise and our BLE beacons don't give enough space for having longer names. In other cases, you might want to do different things.
Okay, thank you.
Thank you very much. So next one is Alex.
Good morning. I'm Alessandro Bassi, and with Marie-Jo, we started some work for vertical agriculture and agriculture 4.0, and basically how to develop a reference architecture, for this field. Now, first of all, I've been working on IoT for 12 years, since 2007. And one of the main problems that I always found is that to agree on what IoT is. I'm quite sure that even in this room, if everybody starts down writing their definition of IoT, would probably be some, I wouldn't say strong disagreement, but not alignment. IoT is related to real objects. So there is a reality. There is something physical, which in this case is a physical entity. This physical entity must have a digital twin. Let's call it digital entity, virtual entity, whatever. How to go from the physical to the digital world? There must be some device. And this device, must be have some sensors and some actuator. That means some computation. That is able to extract some of the properties of the physical object towards the digital twin. And the human user, or whichever kind of user, even a digital one, basically what he experiences is augmented entity, which is basically made by the real and the virtual one, through services, which are actually sitting on resources. Resources are both hardware and software. And these resources, can be on device itself, can be in the cloud, can be anywhere. Now, I don't want to convert to my religion of IoT. What I'm telling you is that where I'm starting from. Hello? Yep. And for a reference architecture, this should be easier, but just to make sure, reference architecture is basically a reference for building compliant IoT architecture. It's a blueprint, basically. And in a reference architecture, there are views and perspectives, I mean, performance, security, scalability, and so on and so forth. And all these different views, I mean, needs to basically be put together in order to find something which is basically the local optimum, I mean, for being a real architecture. Now, in this case, views and the perspectives are used by the definition and the standard definition of them. And let's not go further because otherwise, I mean, 10 minutes will be spent just on definitions. Why were we looking at agriculture in the first place? Agriculture is, I wouldn't say a very laid down domain, but for sure is not the most modern one. And there is huge amount of improvement, I mean, that can be done. When you really go in the field, I mean, and you're working with people, there, I mean, you can see sometimes, I mean, processes and even the computing, I mean, is really belonging to the last century in a sense. And this is, you know, in Europe, in Canada, in the US, I mean, so not to mention other places in the world that are at least less developed than Europe. Of course, I mean, there is lots of advantages, I mean, in terms of productions, in terms of management, of partners, in terms of sustainability, also with respect of using of water, using of pesticides, using of chemicals product, I mean, and to produce fresh products all year round, which are more or less, you know, good, I mean, following the seasons. The case study, I mean, that we use is with a company from Montreal called Nova Farming, and the use case was basically a strawberry production. So basically, we try to develop, I mean, this reference architecture for their specific needs. Now, IoT in general has 9 challenges. Again, there can be more, there can be less, it can be discussed, but this is where do I start from? These 9 challenges are miniaturization, which is more and more and more, harsh environments, devices are out there, so I mean, you know, you cannot control them, I mean, with humidity, with temperature, with chemicals, and so on. Communication, I don't have to explain here what it is. Self-start properties, which is basically autonomic properties or artificial intelligence, and so on. Identification, again, is something I don't have to explain really here. Security, again, packaging, which is basically how to put devices into non-standard material. They can be wood, I mean, they can be metal, they can be whatever. Energy, considering that most of these devices, I mean, are battery-based, so how do you develop almost zero entropy systems? And quality, because of course, I mean, you don't want devices that are giving like whichever result, I mean, all the time, and you need to have some sort of a security, I mean, that the device, I mean, is projecting something good. Now, related to agriculture, I mean, we can discuss about this number more or less, but clearly, I mean, harsh environments is very important because if you put sensors, I mean, in a field, I mean, you don't really know, I mean, what is going to happen there. Communication, self-properties are also important, I mean, as well as packaging, because for sure is a non-standard place where to put a computational device. Other things that are less important, like miniaturization. You know, if you have a field, I mean, it's not important if you're talking about millimeters or nanometers. And also related to energy, I mean, and identification, I mean, this is least of a problem, I mean, related to other fields.
Can you move to the architecture because you're on 3
Yes,
minutes?
sorry.
Yeah, actually, I would skip this one because you have only 3 minutes left.
I have only 3 minutes left? Oh, shit.
Yes.
Very sorry. So centralized versus edge, I mean, clearly in an agricultural field, I mean, we need some sort of edge architecture. And if you need an edge architecture, I mean, we need to have computation at the edge or computation like within the network. Now, for doing that, we need some specific hardware, which needs to be programmable. It needs to have all this stuff you read there. So data filtering, content-based routing. We can use P4 languages and the Hackathon, and you know, they should do at least some data analysis and some messages. Now, If you put basically intelligence in the network, so you're talking about network-enabled artificial intelligence, that's why basically artificial intelligence, if you consider it as a calculation of probability of something happening or not happening according to parameters kind of coming in from an input, basically that's what agriculture needs, right? You have a bunch of parameters and you have to predict how things are going. What happened here? I pressed something wrong. Okay, now this is the architecture, which basically is divided in 4 different layers. One is market-driven decision layer, basically deciding how to push or to slow down, the production of some products, in this case, strawberries. Data layer, and we will see a little bit later, next slide. And this is basically the core work for this working group, because that's where filtering and processing is going through in the network. Production layer, when basically is monitoring what is happening in the field, and then local decision layer, because some of the devices, according to visual analysis and so on and so forth, are able to take some decisions, with respect to what is need to be done. Now, common distributed data layer, very quickly, this is the part, which is more relevant to this working group, and is basically the part when data and metadata is actually filtered, in the network, according to their importance, according if there are errors, according to things which are not basically fulfilling, what is expected. So you can have local nodes, you can have remote nodes, which are connected either in a wired or wireless way. This is really not important, but basically this filtering happened, at network level. And then, issues, can be brought up, to the cloud, if they're important, or they can be resolved, on the spot if it's really something minor, like a little bit more water or a little bit more light. Next steps, basically, we plan to formalize these in a draft, before Vancouver, and some acknowledgements.
Thank you for rushing it. We have time for one question, if somebody has one question. I know that for the people who are doing Klaus, there's a question. Is this, yes, Jeff has a question.
Oh, no, I was just getting ready for my presentation, sorry.
Oh.
Good to say again? We lost you.
I said I was just coming on to get ready for my presentation.
Okay, great. Thank you. So if there's no more question, yes, we are going to go to Jeff's presentation.
Do you advance the slides for me, or do I have a button here that'll advance them?
Yes, I have your slides, so I'm just going to put them now.
Okay.
Hold on. I have problems with my timer, so my timer keeps playing Inspector Morse theme, and it shouldn't be.
Okay, while you're getting those up, I'll introduce myself. I'm Jeff Halpern. I'm with NovaFlow. We talked to you last year about our match action pipeline. We produce a very high performance, 6 terabit switches that are fully programmable, P4 runtime. So this year we're going to talk about implementing those. I run the application group where we take the technology and move it into solutions. So this is kind of an applied research group. We always have a client in the middle, and what I'm going to talk about is one of those projects that we just did with a major service provider where we brought telemetry in. So am I capable of advancing the slides, or do I ask you?
We'll advance them for you if you'd like.
Okay, yeah, next slide. So I'm going to give you a real quick overview. We'll go through these first slides very, very fast. One, we talked about a new use case. It's going to be with INT telemetry out there. This is a very huge deal in the programmable pipeline world, where each packet starts to carry the metadata about what it's doing, and provides completely new opportunities for how intelligence that you gather in the network, how you run the network, compute you could do in the network. In our case, we're going to go against a requirement of how do we figure out latency, which is kind of just the very basic thing. But in this case, I'm going to ask, how do we do it against passive tools? How do we do it against things that aren't INT capable out there? I'm going to introduce the environment we had. We're going to talk about the tyranny of INT data. It's not as great as it sounds. It comes with a high price. We'll talk about that. And then some strategies, some actual ways to deal with that. So next slide. So whenever you talk about telemetry, you're going to get a slide like this. You're going to see pictures like this, which is packets are moving through the network. At every hop, they get data pushed into them. That talks about the telemetry in there. And at the end, the telemetry data gets popped off and sent off to an engine. Looks great, but this is a forklift upgrade. The carriers can't do this. They've got hundreds of millions of dollars, billions of dollars of infrastructure out there. They just can't change it all at one time. So the question is, how do we get telemetry, in kind of an incremental approach? Next slide, please. So another really quick way of looking at this is just to bring anybody in that hasn't worked with it. In INT, as the packet moves through, you get a new header. And in this case, it's talking about going through switch 1, switch 2, switch 3. At each one of those, data gets pushed into that header. Latency is one of the things you can get, but you can pull anything off the devices that can work on this. The interesting thing here is that every participant is a capable INT device. So it has to be up to date on this stuff. Next slide. So our question is, what could we do to deal with things that aren't capable? Now we have a passive device that isn't INT ready. Big problem out there in telcos. They have billions of dollars over in these security tools. Firewalls are the ones you'd know the most, but there's all kinds of security tools out there. So, if you have a terabit of data coming in, you probably have $500,000 worth of security devices out there. So a very simple question is, what's the latency through these? How well are these things operating? Nobody knows. It's tough. So what we've done is said, okay, we've got a new technology, but in INT, but we have an old technology in these firewalls out there. So let's put a wrapper around it. As the data comes in the NovaFlow switch, we create a little private domain where I load balance out to these firewalls and then bring it back. But as we're doing this, I'm going to add the INT data, the telemetry data, but we're going to do it at the switch. We're going to actually capture the latency of these tools out there, but they'll never participate in that. And I think this is the general case of this is, how can you start using the telemetry and think of surrounding now devices that are dumb, that can't add telemetry themselves, but the switches on either side or the PCs on either side that can pack things into them. So next slide. So in our case, what we're doing here, some detail, you can look at it out there, but basically as the packet comes in to the switch, the bottom center is the switch down there, where it says packet broker service. We put a tag on and I put a timestamp on. Then I send it out to the tool farm, and all that Fortinet or Palo Alto have to do is not croak because it has a new tag. It just has to be able to process the packet, do its normal stuff, and have that header pass through it. As it comes back, I timestamp it again, and then we do the standard INT stuff. I pop it off, send it out to an analytics lake, and the packet moves on as normal. Now I've gathered the data out there. I can tell you exactly how much latency that firewall has caused at any time of day, but the tool hasn't had to adapt at all. So again, I think it's a very good general principle. So let's look at
Jeff,
Yeah.
2 minutes.
2 minutes. Okay, so let's look at the downside real quickly. Next slide. The interesting thing here is the data comes so quick. We're talking about terabit solutions. We get millions and millions of packets, so you have to reduce it quickly. Next slide on that. And what it says on the left-hand side is you can start to come up with an algorithm where you weigh the cost of gathering stuff from a packet and versus the value of that, and you balance those out so that you don't gather every observation. You don't put billions of records in your database. You stretch them out and you gather the value across that, and that allows you to now do very profitable or very impactful things, but keep the cost of that down. So last slide. And here's just real world stuff working on there. We have a tool farm. We're driving a terabit of data through here. I have 3 different environments. One where we just did a loop back to show there's no latency. The next one where we have a tool farm, or we have a tool that has a minimum set of security filters going on it, and then one has a full, and you can see the latency pop up on that. And none of that data is being collected actually over on the farm. It's being collected in the network, and value add. So we think it fits very well with how do you add compute into the network. So sorry I went through so fast.
It's fine. Like I said, next time we're going to have more time. We have time for one question.
Tal Mizrahi. So thanks for this talk. I wanted to ask regarding, you mentioned timestamps a few times, and obviously you need accurate timing here. So usually the timer or clock is going to be implemented in hardware. And on the other hand, we know that it's often the case that in these protocols like IOM, INT, each of them uses a different timestamp format. So I wonder, to what extent do you think is it possible to have a completely programmable data plane where you want the timestamp formats to be programmable, but on the other hand, you want very accurate timing?
Yeah, so great question. Thank you, John, for the question. In this case, you have to look at the latency being added by the firewall, which is huge. And so the difference between a software timestamp, coming out of a standard switch, we're on a Trofino switch, and a hardware timestamp coming out of 1588, those values, we're not looking at that level of detail that we need here. So the software timestamp coming right off the Trofino is more than fine. It is 2 or 3 orders of magnitude finer, accuracy than we need to measure the latency. You can have other situations where you need, so if you're doing the timestamping in broadcast, you need that 1588 because you're down to frame by frame, stuff. But in this application, the built-in hardware timestamp on the Trofino chip is more than fine. Does that answer the question?
Yeah, thank you.
Yep. Thank you.
Thank you very much, Jeff. And again, we're very happy that we have you guys in this group because you bring the real world into the discussion. Thank you so much.
Oh, you're welcome. Thank you. Bye-bye.
Next is Michelle. And Michelle was actually was not planned before Saturday, which shows that hackathons work because we essentially connected at the hackathon.
Okay, good morning, everyone. My name is Michel Bonfim. I'm a PhD candidate at Federal University of Pernambuco, and I'm here today to present you a practical implementation in P4 named SFCMON, and it aims to provide an efficient and scalable monitoring system for network flows in SFC-enabled domains. So let's start by defining what is SFC. And SFC means service function chaining, and it is a mechanism that allows another set of network service functions connect to each other and form end-to-end network service through different data centers, ones, and application service providers. And it's worth mentioning that SFC is considered a key enabler for network function virtualization. So it is a hot research topic. Go on. In this work, we tackle the problem of how to provide monitoring test for SFCs in a scalable and efficient manner. So taking this into consideration for SFC purpose, we argue that a monitoring task should take into account all transmitted packets at the same time that keeps memory and processing at acceptable levels. So we propose the SFCMON an efficient and scalable monitoring solution to keep track network flows in SFC-enabled domains. And to achieve its goals, it implements a pipeline of probabilistic data structures to keep track only the large flows directly inside the network switches, thus reducing both overhead layers and signaling overhead. Next slide. So we proposed the SFC as a new SFC component. So we recommend that it should be positioned between the classifier and the SFC function forwarder in order to be possible to process all the encapsulated packets before they are forwarded to the next component. This figure illustrates the SFC processing pipeline. Basically, it works with 3 types of probabilistic data structures, but of course, I'm not get deeper because in the interest of time. But I would like to highlight 2 of them. The first one is count means cat, that is responsible for the detection and filtering of large flows. For this, it solves the E-approximate heavy hitters problem. And the other structure is invertible blue lookup table that it is responsible for keep track the flow records of these filtered large flows. Continuing, I think that this is the best slide of this presentation. We have implemented a SFC prototype as a proof of concept. And basically, it comprises 2 elements, an SFC switch and an SFC controller. And regarding the SFC switch that we highlight in the right side here in the figure, the SFC switch is basically a P4 program, and it is in charge of the SFC data plane. For this, we created a P4 reader for the network SFC reader that or NSH. It's worth mentioning that NSH is responsible for, as used by SFC for interconnect the network service functions, is encapsulation protocol. Besides, we implemented 2 of the main SFC components, the classifier and the SFC function forwarder. And for this, we have used P4 tables, as you can see in the figure. And of course, we provide a SFC reference implementation. And for this, we have used P4 register to implement all the probabilistic data structures that they use. Moreover, we also extend the behavioral model and the P4 compile code in order to support more hash functions in order to the solution works properly. And finally, we have the SFC controller that we implemented in Python, and it used the P4 runtime to interact with all the SFC switches. And basically, it has 2 main functions. The first one, it is responsible for creating and removing SFCs on the underlying infrastructure. And the second one, it is responsible for keeping track the flow records by periodically collecting statistical information from the IBLTs, the lookup tables, from our SFC switches. So, to conclude, the SFC source code is available on GitHub, so anyone can download it and reproduce the experiments. And that's it. Thank you. If you have time, I'm open to questions.
Thank you.
Quick question.
Okay.
I might miss something.
Your name, please?
Yeah, Hao Song from FutureWay. I see you have a component so actually to detect the large flow, but I'm not sure I see any slides talk about what you are monitoring. How do you get what data you are collecting and what you are actually monitoring for those large flows?
Yeah, basically, there's some keep track each SFC, and basically we consider only the 10% of the traffic that is considered large. But are you asking if I perform some experiment with a real data set or no? I don't know if you understand your question.
So all the problem you solve is to detect some large flows, or you also want to have some other performance monitoring? I'm not sure I see those information in your talk.
I just want to keep track large flows because the aim of this work is to run in a real time. So we want to reduce as much as we can the probability data structures. So we have to work with the minimal data.
Yeah, okay. So I think in another IETF draft we submit to the other working group, are we talking about actually you can use some architecture, data structure like Sketch to detect the elephant flows, and you can apply the some function like the int in the previous talk to actually monitor the performance of these large flows, so that make the functionality more rich.
Okay, if you want, you can discuss
detection big flows.
Yeah. Okay.
Dirk, did you have another question as well? Okay.
Okay.
Thank you very much.
Thank you.
Okay, so we're done with the presentations, and now Dirk is going to do like some kind of a mix between the research and the draft.
Thank you. Could some of you take notes at the end of my? Thank you very much. Okay, this is an update of the directions for CoinDraft that we so Jörg Ott and Timo Kakain and myself submitted before Montreal. So quick, can you make it full screen, or can you hit that little box? Thank you.
Hold on. I didn't click the right button.
Thank you. So quick reminder, so this draft is discussing so what we think in network computing or in network really means in the, say, coin research discussions, and explores like different options and compares them a little bit. Also looks a bit at different interesting forms of computing. So Jörg had an example earlier, and tries to create some basis for a discussion. So what coin could or should look at. There is lots of computing in the network today. So we heard a few examples again just before. So things like smart NICs, web servers, CDNs, various cloud platforms. Quite often when we say edge computing, this is typically, what we typically mean is extending the cloud computing concepts, so managed infrastructure to specific hosts at the edge, so co-located to base stations, for example. So we think that so these approaches are applied more or less today, and probably don't need that much coin research anymore. But there's lots of engineering work going on in the IETF, which is great. So one example is mobile or multi-access edge computing, which is essentially managing infrastructure, say in the access network, for example, for running virtual machines in a telco deployment. So this is say a system where you can with a certain contractual agreement install something like a process or a virtual machine that it does something with the traffic. Let's put it like this, and that could provide enhancements for certain applications, for example. So this is a probably rather static environment that could be, in our view, maybe used as a, say, execution environment or something, but that's not something that I think we think the interesting research questions are. If you look at the other side of the spectrum, there's all kinds of super relevant, super successful deployment of application layer streaming and data processing frameworks, typically for the cloud. So these are, in general, application layer solutions that, in the case of Flink, for example, allow you to arrange processing steps in a pipe, for example, that you can program, provide scalability for that, and so on. These systems are really nice. They run well in the cloud, but because they run as overlay, they cannot take advantage, say, of the network that well, so don't have the full visibility. It's a bit like connecting functions through, virtual pipes. They operate on their different namespaces, so the application layer namespace, you often need additional steps to map this to the network. Security was mentioned earlier, is in these cases often centralized because they are designed to work in the cloud, for example. So the draft kind of discusses these different, say, perspectives and tries to formulate a notion of computing in the network that basically could provide a system that allows you to do something useful for applications like, or for frameworks like Flink, but with a deeper integration into the network. And so that's, say, we think one of the interesting research options in this environment to look at how we can integrate or can marry these the different worlds. So useful functions for applications and the networking support to make this run really well in say different network environments. And then look at what you can gain in terms of optimization in these cases. Okay, so quickly to the updates that we included in the latest version. So there is a discussion about service function chaining. So we just heard about monitoring for that. Service function chaining has been designed to chain functions in the telco cloud. So it's called GI LAN. So things that process data with a certain flows in it with a certain trust model. We had a description earlier, and we got some comments for useful extensions. So in general, service function chaining is about flow or packet steering, and it typically encapsulates packets so they can arrive at the right service function forwarder, for example. I think just right now, just in November, a few colleagues published RFC 86.17.7, which is an extension, or a proposed optional extension to the SFC framework that is using one layer of indirection. So it's using a named-based scheme for naming the functions, and then describe how this could be mapped to lower layer identifiers. So it has a bit of ICN spirit in it. And it also specifies how you can, or describes how you can specify hop-by-hop transport between pairs of SFC nodes. So there could be settings where, for example, one pair uses HTTP, another one uses another protocol, so that you could actually use that system to construct compute graphs between application layer functions, because so this does a little bit more than just enabling the IP packet forwarding. So there's a bit, say, bigger idea behind it. And so you could say it could perhaps be used for some of the applications we have in mind here. We also added some additional text on MEC. So as MEC is a platform, we got one comment that it could be interesting to just look at so the combination of multi-access edge computing and network slicing not so much as something where we want to do work in, but just as an example, when you think about something like an assured service quality that you may want to establish in a distributed computing scenario, so that you so network slicing could provide you some kind of QoS enabled forwarding, and that could be something to think about. What could that actually mean for computing in the network? And then finally, we included one example about a system that so my co-authors here and I just built and wrote about this year. And so I'm going to explain this in a few slides now. And so we called this compute first networking distributed computing meets ICN. So it's a coin system, if you want, that is implemented with information-centric networking. And so the idea is that we want to, treat computing as a first-class citizen in a system and make it possible to reason about network computation. So I have a system where you can, scale out functions. So if, like, for example, you have say function that is, popular or needed a lot, you create several instances of that. The system takes care of that automatically. Has a security model so that you have things like confidentiality, authentication, so of nodes and functions. Has a notion of reliability, congestion controlled operation, kind of fail-safe, and should be useful for application developers, so that so in the spirit of what I mentioned earlier with Flink and so on. And so this is not just about controlling packet forwarding, so like through tunnels or maybe through routing updates and so on. This is really about distributed computing, so operating on a slightly higher layer of abstraction, if you want. And so just briefly, the concept. So you can assume you have a set of nodes, so execution environments in the network. They are named with some scheme. Ideally, we want to support different types of execution environments. So in the prototype we developed, we had just one, but in principle, it should be possible to leverage different capabilities. So hardware support GPUs and then select the appropriate ones for a specific function. So nodes could be part of different distributed application context. So they could offer their resources to distributed application A and B, and then maybe arbitrate between those. So in a distributed application system, we assume that we are able to instantiate, invoke functions on that platforms. And then we distinguish between different types of functions or resources. So stateless functions that enable idempotent operation, stateless actors, so that's something that keeps state, and also data. So when we for the decision how to lay out the graph, we also consider where data resides, and so the application semantics and so some resource allocation strategies then dynamically influence the decisions, so where certain functions are going to be instantiated. And so there's a remote method invocation protocol that allows us to implement the function execution, transfer parameters, transfer results back, and so on. And it doesn't make any assumptions on how complex those functions are. So it could be really small ones, but maybe also more complex operations. And one function can also, of course, dynamically trigger invoking other functions somewhere else. And so in a system like that, you have to manage information like where are the functions, so how are the resources utilized or loaded, overloaded, how is the current dynamically observed performance. what maybe additional resources become available. So we did a system that kind of maintains this information in a distributed data structure. And so we are using a system of trying to forward or decide on like function invocation on say next hops or neighbor hops dynamically. So trying to put this into our COIN discussion here. So the COIN elements that we use in that system. So we are managing resource availability and so load information and disseminate that. And so we are using distributed data structures for that, so CRDTs. And so these are shared by the nodes that take part in a distributed application context. We have a transport and remote method invocation model that is using a system called RISE, so remote method invocation in ICN, another piece of work we did earlier. For deciding dynamically, so with a maybe late binding concept where a function is actually going to be executed, we use ICN forwarding hints in this system. The programming and execution environment here is Python. Again, as I mentioned before, the system in itself is general enough that it wouldn't have to be just Python, but we used it in the system. And in terms of categories for computing, we distinguish functions, actors, data, and the naming of a function, or that's done by ICN naming. We have a certain scheme that I'm not going to discuss now, but you can look it up in the paper. So there is something like a task scheduler that needs to understand the say nature of the program, and then basically analyze the resource description and then make decisions. So like where certain functions would be allocated and executed. And so this is a bit of terminology that we are using. So a program, that's the set of computations requested by a user. So I'm describing this because I thought it could be interesting to have some kind of terminology just for comparison, how we deal with certain concepts in this particular system. A program instance, that's the instance of the program that we are currently executing. Function, we use that word for describing a specific piece of computation that can be invoked as part of a program. So data, that is what we mean by function inputs and the outputs. We have a concept of futures. So in the program, when we describe function execution, we get back a handle that later allows us to retrieve the actual computation result. And so worker, we use that term for specifying the exact locus of a function or actor in a particular program instance. And here's an example of a distributed application or program that we define in Python. So this is regular Python code, and so we added these decorators that allow us to describe what type of remote function we are talking about. So like a transparent, financially transparent function or opaque function, an actor, and so we are programming this in the system. All the nodes that participate in one program instance need to have that program. And then, well, as any other program in a Turing-complete system, we cannot predict what function will be called at what time. So this is then dynamically decided. And so the nodes basically share this computation graph. So it is known where data resides, and so what is the chaining of the function and so on. And this graph is constantly updated, so in this distributed data structure with non-conflicting merge operations. So it could be that, for example, here this function called extract features is allocated on node 1 by, say, in one branch of the program. Another branch may locate it at node 2, and so these information, these decisions are shared in this ERDT, and then could be merged with this non-conflicting set merge operation, so that we kind of consolidate this compute graph. Each node has something like we call task scheduler. So that dynamically makes a decision. So when I see in my program analysis, okay, I have to execute this function now next, that makes a decision where this should actually be executed. So it's possible that the function, or it's quite likely, has already been allocated or instantiated on some node, and the system has information for this. It could be, say, in the forwarding information base or somewhere else. Here we are using these ICN forwarding hints to steer the request, so that we maybe know specifically, so know exactly.
2 minutes.
Yeah, I'm almost done. So that we, when we know, say, the identity of a node, for example, where that function is, we can kind of provide that additional information. If we don't know it, then ICN forwarding could take care of that. Okay, let me skip this this example now. The system here is that we developed is a distributed computation framework for general purpose computation. Has this distributed data structure to maintain this compute graph between the nodes. We have some concept of transport and RMI. So thanks to the ICN basis here. And yeah, check out the paper and the source code that's available here at that link. Looking forward, we want to kind of enable more decentralized decision making in that system. So consider more dynamic network and platform load. Maybe think about what, as I mentioned earlier, what QoS could actually mean here. And so have a soft state approach where we can really reduce the coordination and state keeping load. So we have certain mechanisms in ICN that could help us maybe to leverage, say, features of the network system directly and make this quite elegant. So coming back to the COIN direction draft. So when we talk about computing in the network, so this is clearly just more than forwarding packets to nodes, so that happen to live on VMs or processes, or to host VMs or processes. So this can be done today. So what I think is really interesting and has lots of potential is really embracing the idea of supporting distributed computing by trying to leverage concepts and mechanisms that we know from networking and try to build a better combined system. So better than just building better pipes. For the draft, so we want to document some more relevant and representative use cases. Somebody mentioned to me segment routing. I think that is a nice addition. And so we will see this as a contribution that should help the discussion in the group. So we try to maybe come up with terminology and a taxonomy that could be helpful. So the goal is not so much to prescribe the best or one way to do it, but really to help us better to understand the problem. Thank you.
Great, thank you. Any questions?
Yeah, so let's assume you were the chair of the DI-NRG working group. On which basis would you reject these type of work in DI-NRG? Meaning, to me it looks all very similar, and I have a very hard time coming up with a clear distinction between what's proposed for COIN and DI-NRG.
So I really don't get the question. Can you kind of rephrase that bit, please?
I'm saying that I have a hard time figuring out in these proposals, which are all find very interesting, to see why they couldn't happen in DI-NRG.
Because this is about computing in the network, a distributed computing platform. systems like this could potentially use decentralized infrastructure for certain infrastructure services, maybe key value stores or something. But the focus here is really the distributed computing.
So you're saying that DINRG would only, want to take on maybe smaller building blocks and not the whole, because these all look like very much distributed applications, right? So I'm not sure to which level you want to constrain DINRG, and then it's really hard to figure out from, these are just examples all given, right?
Right, but DINRG is really about decentralizing internet infrastructure. So naming systems, for example, maybe potentially routing. As for APKI, for example, this is really about distributing computation.
Yeah, but I mean the distribution of infra. What do you call internet infrastructure, right? What is not going to be future internet infrastructure here, right? So it's
right. So, yeah. Well, I think.
I think a clear delineation or so in a description would help very much. Can I have a second point, or
can I answer briefly?
We have a lot of things. Please,
Hi.
Colin.
Hi, Colin Perkins. If I can just follow up on this. There is clearly, to some extent, overlap between the work happening in this group, the naming decentralization work in DINRG, and some of the work in the ICNRG. I don't see that as a problem. There's no requirement in the IETF that groups are completely distinct and don't, to at least some extent, overlap their work. So I think the focuses are sufficiently different that this is, the small overlaps we have are fine.
just quick note. So from the focus of what these are about, right? So the distributed application infrastructure itself, or so, to me, that's kind of a given, right? So the interesting parts are really what I would like to see coming out are the numeric analysis of, how the network, the latency, the throughput, the distribution, how it's done, right? So the performance investigation, right? So that we also have an understanding of what the network should look like in the future, so that these distributed applications run best, or what performance we can expect with certain type of networks, right?
And we would welcome your contribution if you want to do it.
No, I mean, I'm saying that this is what I would like to see from the working group. It doesn't necessarily mean I have the cycles to do it myself, or even the the background.
Right. So I mean, this is research. I didn't put up the evaluation results here, actually. So please look it up in the paper. We have some limited performance evaluation in that paper I mentioned.
Yeah, we need to move on to the next question. I think the next is Nico.
Okay, it's me. So it's Nico.
Well,
or
you can,
Kuhn.
Nicolas Kuhn, yeah.
And so Nicolas Kuhn from CNES. Thank you for the presentation. Sometimes when we write generic architecture, it's very difficult to see it's actually generic. And maybe sometimes we have one use case in mind. And I think this general architecture, and speaking about distributing computing, that's a relevant use case for interconnected quantum computers. And that's maybe too forward in the future. I'm not sure to what extent it is relevant to your draft. I haven't read your draft, but that may be just another use case you may want to consider to see to what extent the architecture is generic. I'm not sure if it's relevant or not. Just wanted to
thanks.
mention that kind of very futuristic use case that may be relevant to tackle your architecture against.
Thanks. I'd love to talk later to you. Let's maybe, if you have some time, let's talk after the meeting.
Okay, sure.
Thank
you. Can stay. Thank you.
Liang from China Mobile. Thank you for the presentation. It's very helpful. Just a very clarification question. Do you distinguish computing in network and programming in network in terms of your methodology?
That's a good question. Right. So we had this in the previous version. I mean, things like if you're referring to programmable data plane or these kind of things, well, this could be a means for enabling computing in the network in some way. So that's the way how we describe it.
So that means like research on P4, for example, would be also a considered scope in this research group.
Well, I think, I mean, we had seen some computing in the network, say, developments that used P4 or use programmable data plane in general. I think that they are useful. So the question is a little bit, how can you, use these systems to do something, say, helpful for application developers, or quite often what we have seen is like point solutions that demonstrate the merits, so that you can speed up, say, distributed consensus protocols and so on. And so we think maybe the research challenge is also how to leverage these cool mechanisms to design, say, coin platforms that could be used for different types of applications, have maybe something like transport and security in mind. So this is, I guess, so how these platforms could be used.
Can I jump in just for a second? Yeah. Dave Oran, I'm a co-author of the paper here. There are aspects of P4 which are relevant and aspects that are not. So if the research is how do I build a better P4 compiler, I think the answer is no. Right? If the answer is how do I build a better TCAM-based switch to run P4 on, I think the answer is no. On the other hand, if the question is what types of computations can I express in P4 on network style hardware, that's very relevant. So I'll point you to a paper at Hotnets just a week ago by Noah and some other folks that basically demonstrated just exactly what kind of neural network computations could be done and be expressed in P4 on a P4 style in-network computing element, right? So they have a very nice investigation of what are the possible things you could do and what the limitations are. That's very relevant, I would think, from our point of view.
Yeah.
We go to the last question because now we're running out of time. We're right on time, but now we're
just a comment. I'll be quick. So first of all,
your name, please.
Sorry, Tim Mattenberg. So I like those roadmap drafts in addition to agendas. So thank you very much for writing this, and I think it's useful. Second is just a meta comment. I saw that you're intending status experimental, and I know, so besides RFC 2026, there's also a document put up by the IESG for the definition of, or when to choose experimental and when informational.
Oh, yeah.
Okay, so all right, so maybe go for informational. That's all.
Yeah, that should have been the case.
Okay, thank you.
Okay, we have a question from the chair.
We were just curious about whether you are considering bringing your POC into like the hackathon or something. Have you thought about that?
Right. So I think I mean, we're discussing different hackathon activities also in the ICNRG. I think we should perhaps plan this for next time.
Let's coordinate.
Okay, thank you. The next is Klaus.
Okay, thanks. Hi, my name is Klaus, and I'm presenting a draft on transport issues for COIN. So this is joint work with Kunze. He presented our last draft on industrial use cases in, what was it, Montreal? Yeah. Okay, so if we are looking at the transport layer, this is the typical notion that we have in the IETF on the transport layer. So it all computation and all especially modifying application payload is done at the network endpoints. So in the core network, we typically should not deal with transport protocols themselves. But if we are introducing now computing in the network, and I'm in this case referring a bit more to the edge cloud cases, of course, when you ask how is the transport layer then present there, I guess you will have something then like n times end-to-end connections between the let's say the sender or the initiator and then the intermediate compute points. So this is actually a quite simple case. But if you refer to the more, let's say, P4 style programmable data planes, I guess you will not have a transport endpoint in your P4 switch.
And if you think on use cases that are discussed here in the research group and that we have already presented or that other people think of, several interesting transport layer issues come up. And this is what we want to do with this draft. We want to raise the discussion on this. We thought about already suggesting some solutions, but we wanted to first discuss this with the research group and, of course, inviting everyone towards this discussion for providing interesting input in order to think about how can we do that. So what you see in this picture here is how we think of if you do have programmable data planes and you do a bit more than just a bit of traffic engineering with your programmable data plane, but if you're really doing computations and sometimes a bit more heavy computations on your payload, how do you see that on the transport layer? So what I called here is not n times end-to-end connection, but some new notion we think of is like from end to intermediate to endpoint, where you have an awareness on the transport layer of these intermediate compute points. I refer to this as end to I to end. Okay, so there is no simple solution to handle the transport layer issues in the typical internet architecture. So that's why we wanted to raise the discussion. And the points that we want to address in this first version of the draft is, of course, first addressing how do we address these intermediate points? How do you say, I want to have this computation there and there? How do you address that? How about the flow granularity? So on which basis do you do this processing? Is it on a packet basis? Is it on a flow basis or message basis? How do you authenticate maybe the computations? How to deal with security? That's also what the IAB addressed or said should be heavily addressed. And some other transport features that are where the problems are similar than the first ones that I just mentioned. Okay, so addressing who or how do you address these compute points or these intermediate nodes? We can typically do that by IP addresses and ports, of course. So do you address then your programmable data plane like that? Or do you just want to say, I want to have this kind of computation on the data path. I'm not so much interested in where I do it. So it's a bit like a more ICN style, or do I want to have a more location-based addressing? Do you want to have it more in a loose addressing style that you are not really taking care of in which switch it happens? Or do you want to give a strict sequence of where which computation should happen? Is it just a unicast communication, point to point, or can it also be done in a multicast fashion or in a converged cast fashion? This is very generic here, but there are much more problems that can arise than if you really want to do examples. Okay, regarding flow granularity.
And when you had Spring up there, was that the same issues are being addressed in Spring?
Yes. Yeah, that's why I put these pointers in. Of course, there are other research groups or working groups that address several issues. And of course, we put these pointers in to get into discussion with them. Flow granularity. So how about the processing granularity? Do you just do it on a packet basis where you probably have only low state requirements, or do you do it on a more message basis? So for example, we just published a paper on doing an image, a very, very simple image analysis in a P4 switch where you find a certain pattern in a MPEG stream. So there, it's not just working that you look on individual packets, so you have to keep state between the packets. So it's a lot more like a message-based analysis, or do you do an analysis on a stream? So there, it really depends on the application use case, how much state you need, and in order how to reserve the buffers and so forth. For that, and that's for us also a transport layer issue. Another problem is authentication. So probably you want to know as an endpoint who touched your payload and who did a certain computation. So what was changed? Who made the changes? Maybe how can you synchronize the states among these changes? So there is some in our notion also that's also an issue for the transport layer to sync these changes among the different intermediate nodes. Okay, there are also the ACE working group may have some input or some relevant work for this. Another thing is, of course, security. So the trend is going towards fully encrypted traffic, even in headers. So how should an intermediate node work or do computations on encrypted payload? That's also a transport layer issue in my opinion, that you enable that or that you provide solutions for that. So probable solutions could be decryption in the intermediate nodes, but then you can ask, what is the encryption good for? Maybe you have option headers where just that payload that is used for computation may be decrypted with special session keys and so forth, or homomorphic encryption, but I guess nobody wants to have that on a P4 data plane today.
Yeah, but the people at the quantum networking were actually talking about it. So if those things were a quantum computer, it would work.
If we are looking that much in the future, then I guess this could be an option, yeah. Then another question is, how about retransmissions? So for example, in this case, we have a scenario where certain computations have been done on packets in the lower part of the figure you see. So in the when the packet passes here these switches, then these computations have been done on the packet, and then probably the packet is lost. So how about who is responsible for doing the retransmission, and what happens with the state that is in the switches that is relevant on this packet? So if the packet is retransmitted, have these computations, must they be done again? And maybe has the state, must that be revoked? So that's really getting difficult then for certain use cases if you count statistics or the state is relevant on how many packets passed. So I guess we do not want to have the notion of a transaction that is revocable regarding the state in the switches on that. Okay. Similar questions raise when you look into congestion control, flow control, and so forth. So these are all questions. Who is actually in charge of doing something when something goes wrong or when certain things happen in the network? Because we do not have the complexity only at the endpoints, but there may be several intermediate points that do computations and changes on the payload. The thing is, there is no simple solution. There are different features that heavily depend on the use cases you want to realize, and so forth. So that's why we wanted to raise the discussion. So these are the typical use cases that have been discussed in the working group already. So data center, computing stuff in the network. We suggested industrial networks. And of course, you can think of the general internet of doing things, and you see every use case have different requirements and need different transport features here. So the idea of the draft is, since there is no one solution fits all thing, that we raise the discussion, that we get also additional feedback by others, what could be interesting, and that we then think of, okay, do we need new transport protocols? I don't know. Do we just have to extend them, put some options in them? How can we support these things? And yeah, I'm happy to have a nice discussion on this.
Thank you. So obviously there's questions.
Hi, Colin Perkins as an individual. So slightly frivolously, I'm being amused watching people Googling the ACE working group and finding the Asian Captive Elephants group. I think, I mean, you're talking about how different application scenarios and different use cases affect the transport, and I certainly agree that this makes sense. I think the computation model you're using on the intermediate nodes also affects the transport. The more idempotent you can make it, for example, the less state you keep in the network, the easier some of the retransmission questions clearly get and things like that. So I think there's a clear correlation between the computation model and the needs of the transport, and they should be discussed together, and the programming model.
Mm-hmm. I fully agree. Yeah.
There's Carlos, and then Dirk, and then Diego.
Yeah, just to follow up on that, right? So you started with saying if we have P4, then we may not be able to have the classical transport stack, right? So I think the starting point to me would be to classify the, type of in-network compute options that we see now or in the future that are more constrained, and what could we do on them anyhow, right? So what is the compute that could be done? That's the starting point. That's the motivation to me. And I think there was all of these, follow-ups on the transport. I understand that, right? But without a clear understanding what could be computed, it's very hard to figure out which of all these subset of possible transport and session layer features we would need for them. So please have that part up front.
Yeah. Since we are working on several examples and problems on this, we actually ran into these transport issues. So we have several things that we did on the transport that we did with P4, and it always comes up then, okay, what happens then and then? And this is actually nothing that should be solved by P4 or the programming model. But yeah, I agree that maybe the research group should also look into more the programming model. Yeah.
Sorry, just a quick answer. I'm not. I think was it Colin or somebody else? Oh no, it was Dave, right? So it's really the degree of constraints, right?
Yeah.
So in the IoT space, there were RFCs coming up with certain constraints on the amount of memory and CPU cycles, and to the extent that we can qualify these constraints for the nodes that we look into, and then basically say what we can do for compute within those constraints, having that as a starting point, and then we can look into these transport issues required for each of these classes, I think.
Mm-hmm.
Okay, Dirk, and then Diego, and then Dave, and then we're not taking any more questions.
Yeah, I'm Dirk Kutscher. Thanks. Really useful discussion of these transport questions. Just one question. Do you assume, so is the basic computing model that you assume that packets flow from one node to the other and then some modification happens on the packets? Or?
Yes, I really refer to on-path computation. So I do not refer to the edge compute models or things like that.
Okay.
So I really refer to programmable switches and so forth.
Okay, good. So that could be useful for the group to distinguish these different models and have a good understanding. Just quickly, I think you nicely pointed to these. You mentioned these timing issues, for example, in transport. And so, I mean, what we ran into earlier is, I mean, there are really different timescales. So, processing or application timescales, where there's the network, timeout and retransmission timescales. So I don't want to sell anything, but so we have a discussion and an ICN-based solution in this RISE work I mentioned. So that could be of interest.
Okay, thanks.
Thank you.
Diego Lopez. One of the things in the discussion between Torles and you is precisely that this is one of the, I guess, one of the main challenges we have here is precisely making converge edge patterns and let's say general internet patterns, and it is something that is a real challenge. I would say is one of the first things we have to address, because we have here two universes that are talking in that. Apart from that, I was getting a list where you were talking precisely on security and all the like. First of all, don't believe that quantum key distribution at least is not so far. I can't tell you. We are running. I mean, we are running some pilots in production networks. So we could play with this, at least with the keys, not with the rest. And apart from that, is something that there are a couple of additional technologies that could be worth trying here. One is when it comes with multi-context crypto, when it comes with encryption. I know that has been banned, I mean, for very good reasons when it comes, it's a challenge for privacy, etc. In general exchanges. In this context, could have some role to play. And second is something when you mentioned about authentication and how you. I had to look at the ACE. I have not, but in SFC we're working in something that is called proof of transit.
Okay.
That is computationally very simple. I would say it's doable using P4. I'll send it, but it's just to make the announcement. I'll share it on the list, and we can talk about this because I think, in particular, this proof of transit application could be interesting.
Okay.
I'm very much connected to.
Yeah. So regarding the second point you mentioned with the secure multi-party computation, so we do also a lot of work in that, not in this realm, but these are really computationally heavy. So this is nothing I would see today in a switch. So.
But I mean, there is we made some time ago a paper that was precisely dealing with the idea that you have it's similar to the proof of transit. This accumulate calculation. Sorry.
Can we move this conversation offline because we have still two presentations. Quick comment, Dave.
Yeah, pretty quick. So after I read this, I reached a very different conclusion, which is that if you have to consider all of these issues all over again, in this slightly changed context, we may be completely missing the boat in the sense that maybe we don't want to have a transport layer with an identifiable transport protocol for these things. So I would sort of maybe add in here the possible thing that we may be exploring a gigantic rabbit warren that if we pop up a level and say, what do we actually need for a distributed computation to run on these on a given underlying topology without abstracting out transport separately from the computation, we may wind up with something dramatically simpler and dramatically more powerful.
That's actually one of the reasons why we just submitted this issue draft and not suggested certain solutions, because I also got the fear, oh my God, which box of the Pandora do we open now? But we wanted to raise the issues and see the discussion. So yeah, I'm happy to discuss this further.
Thank you very much. So for the last two presentations, we're really running out of time. So please do 5 minutes to state what your problem is, what your solution is, and we'll regroup it either at an interim meeting or in Vancouver. I'm sorry to be the timer here, but time is time.
5 minutes? Yeah. Hello, everyone. Hello everyone, I'm Peng Liu from China Mobile, and I'll give the introduce about the requirements of computing in network. So the draft has been updated to a second version, and in the old versions we proposed 3 requirements, which are new architecture, precision, and ubiquitous intelligence. The major change from last version, we gave more requirements have been collected and categorized them to performance, function, and management. So these are all the requirements we collected in this version. And performance requirement 1 is latency and reliability, which depends on the service demand. The latency can be divided into in-time to on-time, which corresponding to low latency and deterministic latency. For example, for the industrial internet, it may need deterministic latency, such as the motion control. And for the consumer internet, it may need low latency for the gaming and video. And the reliability includes the transmission path and the packet loss rate. And we can use some existing technologies to solve those problems. And the performance requirement 2 is high concurrency. It is because the number of computing nodes increase, and we may distribute some computing and other algorithms to different nodes. So there may be a lot of parallel computing between nodes with the trend of interconnection of everything in the future. And it will bring a great challenge to the network connection. And the performance requirement 3 is security. It's not mean the traditional security about the data or the network. It's just because multi-domain networks may not only be able to communicate with each other, they may need to be analyzed to each other, such as the protocols. For example, the operator's network may go deeply into the vertical industrial internet user site
to provide a better network service. So may bring some convergence problems with operators network and the users network. And going to the function requirement, one is computing aware scheduling. It is meaning to say dynamic computing power matching is carried out not only based on the network status, but also need to consider computing resource to achieve optimal user experience. And the computer resource information can be exposed to each other. And two is function-based addressing. It means the application components deconstructed on the server side and distributed to the cloud platform. So the client only need to consider about the computing function itself, but not where the computing happening, and such as server, virtual machine, and so on. And the third requirement of function is network programmability.
1 minute.
Okay. It's also a very important requirement. So the third kind of requirements are the management. One is cross-domain management. It should guarantee the end-to-end network management to meet the needs of different network topology and performance function, which involves cross-domain network management. And the third is simple management. It doesn't mean that we just need a few functions to management. It is because scheduling and cooperation among the different network demands, operators and users are very complex problems. So we need an effective management system. So that's all the requirements collected in this version. Next steps, one is more analysis about the requirements proper definition according to different scenarios should be done. And we also welcome more discussion on the offline or the mailing list. That's all.
Thank you. We don't have time for questions, so we'll move everything on the list. Thank you.
Okay, so the next will be the report of the side meeting called CFN happened yesterday morning. I know the name is kind of confusing. There's some reasons behind it, and I believe we are close to solve it after discussion this week. So let's move to the technical. So basically, it's addressing the edge computing. There's several use cases introduced in the side meeting. So this is one edge cloud-based recognition of AR. So basically, your AR app on your mobile phone will send an image or stream of images to the edge, and then the result of recognition will come back to your mobile phone. So face recognition is kind of lightweight and simple, but object and emotion recognition can be difficult. Okay, this slide is really what I want to elevate. So basically, the idea comes from that two service characteristics in the edge computing. One is the service equivalence. So there will be hundreds of nodes provide the equivalent service to clients, and due to the edge is kind of limited resource. Typically, there's a number, for example, 10 servers, and also the edge is less reliable than cloud. It cannot be scaled out. So this kind of dynamics means which one is optimal service instance to the specific client or specific users. It can be dynamic, subject to programmability or load, network condition, etc. So it's easy to use Anycast to address the service equivalence, but can we make it more dynamic to adapt to the condition? And I say condition means the network condition and the service condition. So,
Jeffrey, this is like definition of a challenges and another research project. What happened at the meeting? I think this is what we would like to know. And also, I have a question. There is already in this group a draft on AR at the edge and cloud, and I would like really to know what's the difference.
Yeah, I will come to that. So basically, this proposal is try to leverage any cost. The emphasis on the routing part, the path selecting, not how the emphasis on the applications use case. So there are two challenges. One is the flow affinity, because you should be avoid to route different packets of the same flow to different service instance. This can be easily solved if you able to establish a flow table, right? But
Devaran, can I just ask a clarifying question? So you're not considering hot redundancy here, where you want every packet of the flow to be routed to multiple service instances. If you have a high reliability system.
Yeah, flow affinity is, so this kind of hotspot, it depends how quickly it will get hot, right? So if so for one specific flow, it's from this solution point of view, it will not solve that, because it will break the service if we switch that to another one.
Could you conclude with the what happened at the side meeting, and we can discuss this at the interim or later.
Okay. Yeah. So then several the two implementations are introduced. One is based on BGP by my company, and the control plane. Basically, it's associated to address one anycast address and one unicast address to every service instance. So then binding procedures and protocol concept and some preliminary tests introduced. And also there's a presentation from Rich using also they are leverage anycast in context of SFC and NV, but they are using OSPF now. And this kind of summary, so basically the emphasis is on the dynamic anycast. So probably I will call it later CFN dynamicast to differentiate this from CFN ASEAN. Okay, also this a few questions unanswered. For example, what is the service and is the service placement in the scope? But the answer is that the main emphasis is on the path selection, not exactly those service placement, although that's part of the total solution. Also, question was raised about the relationship with this group, research group. And so this presentation was mentioned, and also one of the side meeting chair emphasized that they will focus on the routing optimization. Yeah.
There's been confusion because this work uses an acronym CFN that has a very different meaning in this research group, and we are working on finding semantics that will make sure that we all understand what is what. So we're out of time. I thank you very much. We had eight people on the line at one point. There's 72 people here also. If people haven't signed the blue sheet, please come. Thank you so very much for, again, staying over on Friday. We plan to have an interim meeting virtually sometimes in February. That's going to go on the list. Again, if you haven't signed the blue sheets or haven't subscribed to the list, do it. And I would like to thank all of you, and also obviously my two co-chairs. And we call ourselves the Gemites, and I hope we have a long and Marie-José. So, and I hope we'll have a long life. Thank you.
I'm glad that you guys are talking about name differentiation. That makes me happy. Yeah. Oh, I feel very old after this week.
Thinking of my 30-hour. I'm thinking of my 30-hour day.
30 hours, that's nothing. I mean, I have been